Mars. This rusty-hued sphere, our planetary neighbor, has captivated our imaginations for millennia. Ancient civilizations saw it as a symbol of war and power. But as our understanding of the cosmos grew, so did our fascination. We began to see Mars not just as a mythological figure, but as a world, a place, perhaps even a future home. The appeal of Mars is multifaceted. It is relatively close, making it an achievable destination for our spacecraft. Early telescopic observations hinted at a dynamic world. This enduring fascination is not just about finding life. It is about understanding planetary evolution and our place in the solar system. Mars represents a grand challenge, a test of our ingenuity and resolve. The red planet beckons, a silent invitation to explore. Each mission peels back another layer of Mars's mysteries, revealing a world that is both alien and strangely familiar. Mars is often called Earth's sibling, and for good reason. A Martian day, or sol, is remarkably close to an Earth day, lasting just over 24 hours and 39 minutes. Mars also has seasons, much like Earth, due to the tilt of its rotational axis. These similarities, however, are set against a backdrop of stark and challenging differences. While Earth teems with life and liquid water, Mars is a cold, arid desert. Its atmosphere is incredibly thin, offering little protection from solar and cosmic radiation. The average surface temperature on Mars hovers around a frigid -80 degrees Fahrenheit. The presence of water ice, especially at the poles and potentially underground, offers a vital resource. If we could access and utilize this water, it could provide drinking water, breathable air, and even rocket fuel. The Martian soil contains minerals that could theoretically be used for construction or agriculture. The challenges are monumental. The dream requires a heavy dose of reality. The Martian environment is profoundly hostile to unprotected human life. Beyond the extreme cold and thin air, the surface of Mars is constantly bombarded by harmful solar and cosmic radiation. Astronauts on the Martian surface would receive significant radiation doses, increasing their risk of cancer and other health problems. Creating a sustainable human presence on Mars demands innovative solutions to these life-threatening conditions. We need to develop closed-loop life support systems that can recycle air and water with near-perfect efficiency. Finding and extracting water ice is paramount, not just for drinking, but for creating breathable oxygen. We also need to figure out how to grow food. Technological innovation is the key to unlocking Mars. Power generation is another critical challenge. Solar power is less effective due to Mars's greater distance from the Sun and frequent dust storms. Survival on Mars will not be about conquering the planet, but about cleverly adapting to its harsh realities. The journey to Mars and life on its surface will push the human body and mind to their absolute limits. The long voyage, lasting many months, will expose astronauts to the detrimental effects of microgravity, such as bone density loss and muscle atrophy. Upon arrival, they will have to adapt to Martian gravity, which is only about 38% of Earth's. These physical challenges are compounded by the ever-present threat of radiation. Beyond the physical toll, the psychological impact of a Mars mission will be immense. Imagine being confined with a small group of people in a restricted habitat, millions of miles from home. Communication with Earth will have significant delays, up to 20 minutes each way, making real-time conversation impossible. Providing adequate health care on Mars presents another formidable challenge. This requires highly trained crew members and sophisticated diagnostic and treatment tools. The human element is arguably the most complex variable in the equation of Mars colonization. The dream of establishing a human colony on Mars is inspiring, but it comes with an astronomical price tag. The cost of designing, building, and launching the necessary spacecraft, habitats, and supplies would run into the hundreds of billions, if not trillions of dollars. Sustaining such a colony, with regular resupply missions from Earth, at least in the initial stages, would add significantly to this cost. Who would foot this bill? Governments? Private corporations? A global consortium? Beyond the initial investment, the practical concerns of resource utilization are central to the long-term viability of any Martian settlement. The concept of in situ resource utilization, or ESRU, is key. This means using local Martian resources to produce essentials like water, oxygen, fuel, and building materials. The logistics of transportation and supply chains between Earth and Mars are incredibly complex. Launch windows for missions to Mars occur only about every 26 months. A Martian colony would need to become largely self-sufficient as quickly as possible. Ultimately, the economic model for a Martian colony remains uncertain. Achieving self-sufficiency will be the defining challenge. Our understanding of Mars is built upon decades of robotic missions. Orbiters like the Mars Reconnaissance Orbiter have mapped the planet in detail. Landers and rovers such as Viking, Pathfinder, Spirit, Opportunity, Curiosity, and Perseverance have acted as our robotic geologists. These machines have analyzed rocks, studied the atmosphere, and searched for signs of water. They are our eyes and hands on Mars, conducting vital reconnaissance. What we learn shapes our plans for future human exploration. While Mars beckons, we must balance our cosmic ambitions with our duties on Earth. Our primary responsibility is the stewardship of Earth. Climate change and biodiversity loss demand our attention. Solutions for Earth and space exploration are not mutually exclusive. Responsible exploration should be our focus.